All right, let's get into it. Today, we're crashing head-on into the physics that explains everything from a wild ride at the amusement park to your daily drive to work. We are breaking down Newton's first law of motion.
You know that feeling, right? You're just sitting in the car and then the driver slams on the brakes. Your whole body just gets thrown forward. Well, that lurch, that thing we've all experienced, it's not just a weird feeling. It's actually the key to understanding a fundamental law of the entire universe.
And to really get a grip on that lurch, what better place to go than the amusement park? Yeah, let's talk about bumper cars.
This right here is the whole concept in a nutshell. Notice how it separates the two things, the car and you. The car gets hit. This outside force makes it stop dead in its tracks. But your body? Your body wants to keep right on going. It's resisting that sudden change.
So that tendency, that resistance to change, it's not just some random thing. It actually has a scientific name, and it was first described by the one and only Sir Isaac Newton way back in 1686.
So this is the official formal rule. But what does that actually mean in plain English? Basically, things just like to keep doing whatever they're already doing. If an object is just sitting there, it wants to keep sitting there. And if it's moving, it wants to keep moving in a perfectly straight line at the exact same speed. And that tendency, that stubbornness, has a name: inertia. This is the absolute key property behind the law. It's why a lot of people just call Newton's first law the law of inertia. It's an object's built-in desire not to be messed with.
Yeah, I love this way of putting it. The most crucial takeaway is that inertia is this inherent laziness. It's this deep resistance objects have to being sped up or slowed down or turned. It's literally the reason you lurch forward when your car stops.
Okay, so let's dig a little deeper here. Does every single object have the same amount of this laziness? I mean, is it just as easy to stop a little pebble rolling down the street as it is to stop a giant rolling boulder? Probably not, right? Let's think about it with this really simple example. You see an empty bucket, you give it a kick, it flies, right? Easy. Its motion changes in a big way without much effort. Now, fill that exact same bucket up with water and try to kick it. It's way, way harder to get it moving. Why? Because it has more mass. And there it is. That's the direct connection. The more mass something has, the more inertia it has. Simple as that. The more stuff it's made of, the more it's going to resist any change to whatever it's currently doing.
And wow, this chart just perfectly illustrates the real-world difference. Look at this. You've got a car and a huge freight train both moving at the same speed. The car, well, it can stop in about 65 meters. But the train, with its absolutely enormous mass and all the inertia that comes with it, it needs over a mile, 1,600 meters, to grind to a halt. Insane.
You know, this brings up a really good question. If Newton's law says an object in motion wants to stay in motion, why does everything on Earth eventually stop? Right? If I slide a book across my desk, why doesn't it just keep going forever?
Think about a baseball player sliding into second base. They're all in, a ton of forward motion, a ton of inertia. So, if the law is true, what's the unbalanced force that just brings them to a grinding halt in the dirt?
And the answer? The culprit is friction. It's this invisible, unbalanced force that is pretty much always acting on things in our world. It's the force between the player's uniform and the dirt on the field that works against their motion, and that's what slows them down.
So yeah, friction is always playing defense. It's always pushing in the opposite direction of motion. It's what you have to push against just to get something moving in the first place. And it's what steals a moving object's energy, turning it into heat. Honestly, it's the main reason Newton's first law isn't always super obvious in our everyday lives.
So, let's bring this all together. Why does any of this matter outside of a physics class? Well, understanding inertia isn't just an academic exercise. It's literally a matter of life and death, and it's something engineers have to deal with every single day. This table really says it all. In a bumper car, you've got maybe a simple lap bar, but in a real automobile, you have these incredibly complex systems. Why the massive difference? It's all because engineers know your body has inertia and they have to design for it. Let's walk through it. First, a collision happens, and this huge unbalanced force stops the car almost instantly. Second, the car stops, but your body doesn't know that. Your inertia keeps you moving forward at, say, 60 miles an hour. And third, that's where seatbelts and airbags come in. Their entire job is to apply a new force to you to counteract your inertia and bring you to a safe stop along with the rest of the car.
Okay, so let's end with a little challenge. Let's put you in the engineer's seat. Based on everything we've just covered, Knowing that objects resist changes to their motion, how would you protect this model? If the car suddenly stops, what's the model going to do? If the car takes a sharp right turn, which way is the model going to try to go? Your solution, whatever it is, will be a direct application of Newton's first law.